to San Jose or Vallejo?
Oh, San Jose. Yeah. Our conferences can never be in Hawaii or something.
I don't know. Let me tell you. We actually had a conference in Palm Springs one time. Yeah.
In August, actually?
May. It was May. It was perfect. All the way from the East Coast to...
Okay, so everybody who's back in time, try these two out real quick. It's a little bit different. This is nicer. It's got some concrete numbers to put in there.
I have just one question. From the very last problem we did, the one that turned inverse was the same. Would it just count as repeated or something like that? What would you say?
It's inverses itself.
And that's fine?
Yeah, so if you say what's the inverse of 2x, it's x over 2. What's the inverse of 2 over x? It's 2 over x. It's not a big deal. It's not. Yeah. It's interesting, and you know what it means. It's got to be symmetric, so when you reflect it, it ends up on top of itself. But beyond that, it's not, not like major yet. So I would suggest on these kind of problems, we did the hard stuff first. This is the easiest thing. This is where you have actual numbers to plug in. So what are you going to put into F? G of 3. So what do you want to figure out first? What the hell is G of 3? And then I can just plug that number into F, right? So actually, I kind of recommend do G of 3 over here on the side, and then plug it in to F.
It's 1.
0.
Yeah, so G of 3 is 2 over
1.
Yeah, 3 minus 1. So 2 over 2, it's 1. So what am I taking F of?
1.
1. We just figured out what G of 3 is, so I'm going to take F of it, F of 1. Good. So F of 1 would be 1 squared minus 1, 0. So anytime you have numbers you can use, it's always going to be easier. It's the exact same idea, except now I can figure out the number that's going to go in here. So it's a little bit more concrete. So what do you want to figure out first here? If I knew what f of 0 was as a number, I could just plug that number into g, right? So it makes sense to start with f of 0 is 0 minus 1 is negative 1. So then this says, what's g of negative 1? Yeah, so 2 over negative 1 minus 1. So I'm just plugging a negative 1 in. 2 over negative 2, negative 1. Kick ass. And then one last one. So let the number ones be easy. They should be nice, or nicer. Let me say that. One last thing about the more abstract ones. Can you tell me what might be true about these two?
Inverses.
Probably inverses, right? So let's see what happens if you plug a function into its inverse. Some of you guys might realize what's going to happen. If I plug, I'm going to plug g into f. So whatever g does to x, It's going to change it. F is going to undo it and take it back to x. Whatever g does at x, F is going to undo it. Let's see that happen. Plug that into that. So what am I plugging into F? G, which is? So I'm going to put that there. And plug it into F. So twice x minus 3 over 2 plus 3. The 2's cancel. X minus 3 plus 3. X. And why does this make sense? What would F and G do to each other if they were inverses?
Cancel each other.
Cancel. What would you be left with? X. Well, we just proved it, right? If I put an inverse function inside of its function, they're going to cancel each other out and leave you with the inside. We already know that. What's the cube root of x minus 1 cubed? Yeah, because that function kills that function because they're inverse functions. I'm left with the inside, right? We already knew this. We just didn't see it in that form. Okay, cool. Yes, ma'am.
Wait, so those two cancel out, and then you did negative 3 plus 3?
Yeah, the 2's cancel out, so then I get x minus 3 plus 3, right? And that is just x. So this is a way to show that f and g are inverses. If I ask you, are f and g inverses? The quickest way to do it is plug one of them into the other one. And just see if it comes out to x. If they cancel each other down to x, they are inverses, period. Right? So proving two things are inverses are easy. Right? Okay. So that's the last bit of section 14.1.
Only 4 things.
So is that a good way of checking
Yeah.
if you have an inverse?
Yeah. So if I ask you to find the inverse of something, if you have time on a test or something, you can plug what you think is the inverse into the original and see if it does come out to x. Right? What sucks is if you make a mistake there, but then you think you're wrong, you're actually not bad. So, somebody called for the new function. We're definitely going to do it, and we're going to learn its inverse today too, and then we'll see what's going on here in terms of time. So section 14.2, we've done so much with variables. There's one thing we haven't done with them yet. Exactly. Right. So we put them underneath numbers, like we did 2 over x, which is only inverse, which is freaky. We put them inside of roots. We've done all this weirdness. But what we haven't done yet is seen what they do in the exponent themselves. So I know if I have f of x equals x squared, that's a parabola. Hello. just let it out. Like x plus 2. Don't you blow it up. So that's not what I'm talking about. That's old news. What I'm talking about is turning that thing around, making it 2 to the x. Now that's not something that we can't handle. We know how powers work. What'll be freaky is when you learn like the sine function I had up here earlier. That's an entirely different function that you've never seen or worked with before. This is just has the variable in a spot in a function I know. I know exactly how to do powers. So how would I graph this thing? If I have a function I'm not sure exactly what it looks like, what do I make?
A graph.
How do I make the graph? A table. I give myself some points to plot, and then I connect the dots, right? So what can I plug in there? Let's start, let's do this. What I always do is I at least do -2, -1, 0, 1, 2 when I have a function that I don't know. Put some negatives, put some positives, definitely put 0 in there and see if it freaks it out somehow. Right? Because I love it when people do a parabola and they only do the positive points and then they say, it's a straight line. They did some negative points, they realize, no, it's not a straight line. So you have to do both. So if I put a -2 in there, what's 2 to the -2?
1.
Yeah, the negative means flip. 2 squared is 4. So what's 2 to the -1?
1/2.
1/2. So I'm just putting that in, right? Nothing new there with that idea. If I plug a 0 in, what do I get? 2 to the 0 power is 1. 2 to the first power is, it's crazy. 2 squared is kick ass. What's going to happen if I keep making bigger and bigger negative numbers?
This thing never reaches 0.
It's going to get smaller and smaller, but it's never going to get 0 because the top is always going to be 1, right? 2 to the negative 18 billion is 1 over 2 to the 18 billion. That is stupid small, but it's still way bigger than 0. Believe it or not, there's an infinite amount of space in there. That blew somebody's mind. Look at 2, negative 1, 1, 2, 3, 4. I'm going to get some good room for some. That down there, cool. So no matter what number I put here, when I put a 0 in, it's always going to come out to be 1. Unless I put a 0. Not allowed to put a 0. So that's kind of like standard for these kind of this is called an exponential function. Kind of makes sense because the variable's up in the exponent. And I just plot these other points. So negative 2 goes to 1/4, which is half of a half. Negative 1 goes to 1/2. 0 goes to 1. 1 goes to 2. 2 goes to 4.
That's got
Yep. So if you ever watch a horror movie, The Blob, and the scientist says it's growing exponentially. This is what they mean. It's doubling every hour or something. Or a virus is spreading exponentially. The area that the virus is in doubles every hour. That would be exactly this function. Right? First hour, there's 1. The second hour, there's 4. The third hour, there's 8. You guys kind of with me? That's the doubling function is another way to look at that. So what does this thing look like? This is just going to go forever up. Like Chris said, it's going to go skyrocket. This is going to get really close to 0. And what do you call that kind of thing? Like it's really close but never gets there.
Close.
It's called, it starts off sounding like, it's going to be something bad to say, asymptote.
Yeah.
So we say it's asymptotic at 0. There's an asymptote at the x-axis, the y equals 0. Crazy. So every single exponential function, if I put a 3 there, it would just grow quicker and it would shrink quicker, but it would have the same form. Are you with me? So now we know this form. We know what a square root or any even root looks like. We know what any odd root looks like. We know what any even power looks like. All these forms we're kind of learning are going to really become very important in pre-calculus. Yeah?
Are we going to do the other thing that you were talking about, the other section, that it shows like an opposite? So like switch out the signs for...
Oh yeah, the minute you learn any function, you can start flipping it around and moving it around. Let me see if you guys can do this. So what if I had, let's say h of x is 2 to the x minus 1.
So it moves to the right one.
What would it do to this graph?
Moves it to the right one.
I love it. All the x's can now be 1 bigger. So the whole thing moves over. Remember when it's in with the x, it's the opposite of what's there? It's the same idea we looked at before. We're talking about parabolas and the vertices moving. So this purple function would be every point here goes 1 over. Let's check. What do I get when I plug a 1 in? 2 to the 1 minus 1 is 2 to the 0 is 1. So that works. So I just move every single point, goes over 1, over 1, over 1. So now I get the same form, just moved over by 1. Kick ass. So you can shift any function. You just take x and replace it with x minus 1. Suddenly the whole thing shifts over to the right one. If I would have put x plus 1, it would have shifted backward. Kick ass.
Now will we go ahead.
It never touches 0, right?
Still never touches 0. The only way I could make it touch 0 is if I took it and shifted it down. Then it would have a new thing it would never touch, but it would go through 0. If I shifted this whole thing down 1, where would the asymptote go? It would go from 0
That's a -1.
to -1. Now that would be the asymptote, and it would come in and get really close to it. Cool.
Now what would that look like? The equation to make it do that.
Oh. So my equation is 2 to the x. I'm running out of letters to use. Let's use c of x. And I want to make all my outputs 1 less. That's my outputs right now. How do I make them 1 less? Like that.
So it's still just...
So that would be, take this whole thing, you do this in blue, take that, take it down by 1, take that down by 1, and down by 1.
I wasn't sure if it was going to be up in the exponent again.
Well, that's this guy. That's right. Freaky.
So it's the same with how we were doing the graphs.
Talking about where the vertex moves to, exactly.
It's at the end, just like that seems to be. It's similar to what we did last
Yep.
chapter.
Yep, exactly. Let's see if they do a lot of that stuff to you. Oh, yeah, they do a little bit of that stuff to you. Cool. Okay, so the only thing that really can change that, I mean, the basic form is the same. I can move them around a little bit. The only thing that's going to change, of course, is going to be the base that they use. Right? So if I used, if I had f of x as 4 to the x, if I want to graph that thing, I can make a little table of values. I know what the form is basically, so I don't have to do as many points now. I can maybe do 3 points. That's what I call my anchor points, -1, 0, 1. So if you know what the shape of something is, you don't have to do as many points. You just have to do a few and then fill the shape in. So I had to do 5 here because we didn't know what the hell it looked like. Now I know it looks like that. Let me just do 3. When I put -1 in, I get 1/4. When I put a 0 in, I get 1. Put a 1 in, I get 4. That's crazy. So -1, it's 1/4. 0, it's 1. 1, it's 4. And then I just fill in the shape. Asymptotic back there, and then it just explodes in the other direction. Asymptotic.
So the inverse is probably just the square x over x root of 2?
No, thankfully. No. We'll see what the inverse here is in a second. What do you think would happen if I did that? Put a negative in there for the x.
Then it would be it's just the opposite of whatever you say x is.
Yeah, so if it took -1 to get to 1/4, now it's going to take 1 to get to 1/4. So what's really cool is x is the domain. It relates the left and right. So if I make x negative, it's going to flip left and right. If I make the function itself negative, it's going to flip up to down. Because what does y control? Up and down. Does that make sense? If I make x, put a negative on the x, it's going to flip from left to right. It's going to flip around the y-axis. Because x controls left and right. Put it on the outside, that's making y negative. Now it's going to flip from up to down. So this one would look like 1 would go to there, -1 would go there. It just flips that way. Where am I going?
Back in.
Oh, I went the other way. Okay. Wow. So it just takes that blue line and flips it.
And that's the negative x, correct?
Yep, that would be 4 to the -x. If I wanted to do -4 to the x, that just takes all the old outputs and makes them the negative of what they are. So that's now there. That's now there. So it just takes that blue line and flips it around the x-axis. So not surprising we call those reflections. Right? So one little piece of this section of homework is going to be graph, 4 to the -x or 2 to the x minus 1, and you just have to shift it around. The other part of this section, this is all about graphing for the most part. The other part is going to be, hopefully you let it be not too bad. That's what I used to. The other part is going to be not really word problems. It's just going to give you a function. So for example, they say, blah, 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 blah. Here we go. Beautiful. Bacteria E. coli. So if you have 3,000 bacteria somewhere to start with, the number that you have after so many minutes is given by this equation here. So really, this becomes a problem of, can you put that in the calculator correctly? So they say, okay, how many would you have after 6 minutes? So you'd have to do 3,000 times 2 to the 6 over 20. So it gave you a major hint there. So you put it in there exactly like 3,000 times 2 to the parentheses 6 over 20. If you don't put parentheses, it's going to do 2 to the 6 and then divide that by 20. And that's not going to be good. You want to put that parentheses so it knows to raise 2 to that whole thing. Let's all try it out. See if we get the same answer. I have a calculator. So what do you guys get?
13.5.
Who what?
13.5.
3,600.
Yeah, 3693.4 blah blah blah. So after 6 minutes, you get almost 700 more bacteria. So the bacteria population is growing exponentially. Right? If you made the mistake of not putting in the parentheses, that's where you get. Oops. Shit. Can't make a mistake, right? That's where you get 9,600. So that would be not. You got to put these parentheses in. Okay, cool.
It's still the same.
Yeah. Oh, well, you've got. No, of course. I think more and more of you might have. If you have a calculator where it actually goes up to the exponent, it doesn't look like this when you do it, but it actually puts a number up in the exponent. Does anybody have that kind of calculator? Or when you do square roots, if the square root kind of symbol gets bigger and bigger.
Yeah.
All right, that's the newer RAM on the calculator. It's the older calculators didn't do that. The older calculators would just have a parenthesis. Right? If you have that, you definitely need the parentheses. If you have the one that goes up in the exponent, you just don't come back down until you get the whole damn fraction in there. You don't need the parentheses then because it actually puts it up in the power. If you put the parentheses in there, it's still going to work. So you just be careful. I always forget about that the update, because I don't have that on my calculators. Okay. So that's really all section 4.2 is the graphs. So now we know the basic shape of exponentials. So you're going to have to shift them around a little bit. And then a few where they give you the equation, you just have to plug something in. So don't look at that and say, word problem solution. No, you just got to plug a number in, make sure you plug in the calculator correctly, you should be fine.
You can do that on the test, huh?
What's up?
You can do that on the test, just plug those in and then do it on the calculator.
Of course, yeah. So where it gets more interesting is if I said right now, if I ask you, how long will it be until I get 18,000 bacteria? We can't do that right now because that would require me to solve for t, and t is up here.
Yeah.
So if I ask you, how long will it be until I get 18,000 bacteria? We'll have to say the number is 18,000, 3,000 times 2. We don't have a way to solve for t because we don't currently yet know the inverse of an exponential. So that's the next section. I'm going to get into that right now. So let's put this right here. I want to do that problem now. I don't want to know how long it's going to take. Okay.
But we don't want to know how much.
It's too bad. I do. It's part of my world domination plans is to grow some E. coli. So I need to know. Okay. So the really funny thing is, you guys know, especially because we talked about it, but even before you took this class, you know what a square root was. I hope all of you did, actually. But that's a symbol that had to be picked somewhere in history. There must be some reason I'm doing this spiel. So this symbol, you know what it means. And you've internalized the question that it asks. So math really is a foreign language. It's basically shorthand language, really. If you can internalize what the symbols mean, you can do the problems very simply. People have trouble with what we're about to talk about because they don't realize that's part of what you need to do. So when I say, what's the square root of 49? The answer, of course, is
7.
because I know square root is asking me, what does it take 2 of to make 49? You got that in some form, grammatically different or whatever, in your head. You know what square root symbol is asking you for. But if I were to write log base 3 of 9, some of you guys might be able to ask me, but right now, what? 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 Are we chopping up freaking, what's happening? Right? So we just have to talk about, well, what the hell is this thing asking us? And I like to relate it to square roots, because square roots and log are both things you have to think about backwards. I didn't actually do something to 49. I thought about it backwards. What would it take to make 49? I have to do the same thing with this. So let's kind of build our way up there. We're going to kind of do the same thing we did earlier, because what we're doing right now is we're trying to find an inverse function for an exponential. So let's kind of do it the way we did earlier. Start with 2 to the x. We did that graph earlier. So let's recreate that graph real quick. 0 was at 1, 1 was at 2, negative 1 was at 1/2, and then that's basically the graph there. Is that cool? So I know what the inverse function is going to look like. Somebody help me out. What's going to happen with the asymptote if I flip it? It's going to go from the x-axis to the y-axis, 11. So now this is going to be the asymptote for the inverse. What points does this function go through? It goes through negative 1, 1/2, right?
1, 0.
0, 1, and 1, 2. So what points are my inverse function going to go through?
1.
Yeah, 1/2, negative 1, 1, 0, 2, 1. So let's see. So my inverse function is going to look like 1/2, negative 1, 1, 0, and 2, 1. So that's looking like it should. Right? Don't they look like they're, especially for me, that's really damn good for me. How many so far? So this is kind of weird. We know what this function looks like before we know what the hell the function is. We don't know what function this is. It's the inverse of that, sure. So let's see. Let's at least do this a little bit. I'll show you how you can get to a real good dead end, and then we'll talk about it. So if I start with y equals 2 to the x, how would I try to find the inverse? Switch. And of course, that's exactly what the inverse function does. It puts this into the y value, right? So if I put negative 1 in for y, I get 1/2 out for x. So in a way, that is the inverse function, but it's not good. I want to be able to write f of x equals something. I want to know what that function looks like. And right now, I have a function of y. I can't solve that, because I need to know the inverses to be able to solve this. It's kind of weird. So we just have to give it a name. It's much like we know what this symbol means. Right? So if I have y equals x cubed, to find the inverse, it would be x equals y cubed. Stay with me now. But we know what to do there. What's the inverse function of cube? It's cube root. But we had to come up with a symbol. We wanted a symbol that meant, what does it take 3 of to make this? I want a symbol, and we just chose the cube root symbol. So we can capture that 3 there to show that I want 3 somethings. So here, we got to do the same thing. We want to write a symbol for what this is asking. And what this is asking is the output is going to be the power that 2 needs to make this. Let me say that one more time. The output is going to be the power that 2 needs to get this. So the symbol that they decided on.
Log.
Yeah, it came from Frank Log. Yeah, no, he did. I have an idea. So the symbol, exactly the same idea. If I showed you that today, you would all be as freaked out as you are when I write this down. Because this is just new. But it's a lot like the symbol cube root. The symbol, they could have made a box around x with a 2 on it or something. It could have been any symbol they wanted to, and as long as everybody agreed what it meant, we could go forward. We weren't there to say log's a little freaky. We weren't there. Existential Logarithm, which is Latin for something or another. I can't remember. Arithmos is like arithmetic related. Log, I can't remember. It's like study of or something. Don't know my Latin. I think you'll forgive me. But so when I see this, if I do some computations with this, I just have to know what the question it's asking me is. So the question that this symbol asks me is, what power has to go on the 2? Remember, that's exactly what the output is going to be. What power does the 2 need? What power does this base number need to become this? What do I have to raise 2 to get 8? 2 to the 3rd power. So the answer is 3. So if you internalize that question, then logarithms are easy as hell. They're just asking you, what power does this dude need to become this? What power does this dude need to become this? So these mean the same thing. These two things here. So what would, let's just do some rapid fire stuff here now. What would log base 3 of 9 be? It's not asking you what do you multiply 3 by. We've already got division. Logs are powers. So raise 3 to the 2nd power to get 9, right? 3 to the 2nd power is 9. Logs are all out of powers. If they were about multiplication, they would just be another form of division. We've already got division. We don't need that. So what's log base 4 of 64? 4. How many 4s does it take to make 64? 3. You kind of with me? I don't know if the problem was do you not know the question this is asking yet, or did you have trouble figuring out how many 4s goes? I don't know what the problem was there. You think to yourself, how many of these does it take to make this? It takes 3 4s, and actually when I say make, I mean multiply the b. So it's very much like a root.
So it's not. It's just like if it was log 5, 125.
Yes. Log 5 and 125 is 3 because it takes 3 5s to multiply to be 125. Yeah. You with me?
Yeah.
This is very similar to roots, but they are not the same thing. They are completely not the same thing, but they are very similar. So what about something a little freakier? What's log base 8 of 1/64?
Negative.
Good. It's got to be negative because it's flipped. And what do you do to 8 to make 64? So it's got to be 2, but it's got to be negative 2 to make it flip. Right? How do you make 8 become 64? What do you raise 8 to make it 64? 2nd power, and to make it flip, it's got to be a negative power. So a logarithm is a power. Logs are powers. They're the powers that their bases need to become the number on the inside. So when we get to properties of logarithms, all the properties of logarithms are exactly the same as the properties of powers. Why? Because logs are powers. It's kind of cool. Let that be cool. You'd only have trouble with it if you don't know the properties of powers, in which case you should not be in this class. So some more rapid fire stuff here. What's log base 111 of 1?
0.
So what's the question you're asking yourself? What's the question that this asks?
1.
No, come on.
111.
What do I raise 111 to get 1? That's the question the log always asks. 0. So log base anything of 1 is 0. Well, almost say that. So what's log base 7 of 7? 1. Take guess. Okay. And here's a little freakier one. What's log base 27 of 3? 27 cubed is not 3.
Negative.
It's not going to be negative.
1 over 1.
I'm not multiplying 27 by something to make it 3, otherwise 1/9 would be right. I'm raising 27 to something to get 3. So here's something. What root of 27 is 3?
3.
Third root. And how do you write a third root as a power? 1/3. So that's the answer. 27 to the 1/3 power is 3. Because the cube root of 27 is 3. Now. Does everybody sort of get the idea? Now that was the freakiest one yet. But let me talk about this a little bit, but I want to make sure you guys were cool before that?
Yeah.
Most of you? Yeah. Okay. Speak now or hold your peace for a little while. Let me see if some of you guys understand this. The only time you're going to get a negative answer is when this is less than 1.
0?
The only way you're going to get a negative answer is when the inside thing is less than 1. To get a fraction, the inside thing's got to be less than this, but not less than 1 yet. I don't know if you guys kind of see that. Do you have to understand what I just said to be able to do these? No. But it is a cool little thing to realize is true. Because when you look at that, I understand why you think it's going to be negative. But 27 to the negative first power is 1/27, which is way smaller than 3. So it's not going to be, it's going to be some kind of root. I want to cut 27 down. I don't want to go past 1, they flip it. I don't want to do that. I want to just go to 3. I want to cut it down. Now, obviously, I'm thinking really nice. If I put a 4 there, could you do it? So obviously, right now, we're just getting a feel for what log means. I could just put a 4, then the whole thing goes to hell. You can't do it, right?
So log 25 is 1/5 or no?
No. It's not 1/5 times 25. It's 25 to what power makes 5? How much do you have to cut 25 down multiplicatively to get 5? Half. I got to cut it in 2s. I got to cut 27 in thirds multiplicatively to get 3, don't I?
So in log 125, 5 would be 1/3.
Say again?
Log 125.
Yes, log 125 of 5 would be 1/3 because I got to take 1/3 of 125 multiplicatively, 5 to get 5. You may let it sink in slowly because this is the freakiest one. Our brain kind of gets used to this, but then it kind of goes, what? Because you got to allow roots to happen. Roots are powers. Since the answer is a power, I could have roots help me get there.
You're going to show us how to put this in a calculator?
Maybe.
What's easy? That's log?
No.
No.
Yeah, it's awesome. There's no
It doesn't do that.
log-based anything. So we have to talk about.
No, there's a lock button, but it doesn't do what you think it does.
Don't worry, we'll get there. I'll show you before we leave. Because real quick, how do you put in there? If you don't know there's a root button, how would you do 7th root of something? You could do that as 8 to the 1/7. You got a log-based something? No.
I told you.
That's awesome. L5 means like a whole list. So you're trying to put a whole list of numbers in there. It's going to freak out.
I will figure it out.
You won't because it's not on there. So if you do figure it out, I'm not sure where you are, but you're not in my universe.
I'll figure it out.
So let me see. Let's do one little thing here. Yeah. So if I ask you to, oh yeah, we're not there yet. If I ask you to graph a log, it's a lot like graphing a cube root. You have to think backwards. But to think what number is a cube, that I could do the cube root of it. So here you want to put numbers in here that are what? What's a good number to put in there?
0.
Zero's bad. Because what's a logarithm look like? Where's the asymptote? At 0. So can you put a 0 in? No. You can't raise something to a power and make it 0. If you raise something to a negative power, you can make it very small, but you can't make it 0.
So 1.
1's a really good idea. So, How would I get what would it, if this is 1, what's the output? What log base 3 of 1?
0.
Good. Because 3 to the 0 is 1. I like it. What about 1/3? What's log base 3 of 1/3? -1, yeah. Whatever raise 3 2 to make it 1/3, negative power so that it flips. And then obviously 3 is a good idea. What's log base 3 of 3? 1. Cool. And then if I wanted to do anything after that, I just have to make sure that it is a multiple of 3. It's a power of 3, right? 3 times 1 is 3. 3 times 3, 3 times 3 is 3, right? So I want 3 times 3 is 9. So what's log base 3 of 9? 2, because it takes 2 3s to make 9. So forth, right? So when I got to graph this, 1 0, 1/3 -1, approximate 1/3. 3 goes to 1. 9 would go to 2, so it takes forever just to get up to 2. So it really grows very slowly back out there. Grows slower than a root would. And they grow pretty damn slow. So kind of makes it, if exponentials look like this, logarithms got to look like that. They have to be their flip, their mirror reflection. So section 14.3 is where we are. It's going to ask you questions like these, and it's going to ask you to graph a few of these. Cool. Let's see, the only... Oh, here. Here's kind of an important skill. If 3 to the second power is 9, I can represent that logarithmically as what? Base. Good. Base 3 of 9 is 2. So just remember. Now look how these are inverses. The input here was 2. The output here is 2. That's inverses, isn't it? One guy's input is the other guy's output. That's what inverses do. The output to this guy's 9. What's the input of the other guy? 9. And the base here is 3. The base here is 3. All right, that went over really well. Okay. So you have to be able to do it both ways. Going from logarithms to exponential is easy. Let it be easy. I have no problem saying that. I don't feel bad if you don't agree at first. You will. Logarithms to exponential is easy. Log base 7 of b equals d. How would I rate that? What would
D to 7.
7 to the d. You can always draw these little 7 to the d equals b. Because what's the answer to a log is the power that you need on the base to make the dude inside. That's what that means. So it'd be 7 to the d equals b. All right? Something we all know, that's true. And going the other way can get a little tricky. So if I had log, if I had 11 to the 1.4 equals m, how would I write that logarithmically? Good, the base is 11. That's a good place to start.
11 to the m.
Good, this guy's output is this guy's input. Bless you.
1.4.
Good, and you know that the answer to a log has got to be the power I saw there, right? The log is the power. You can always check yourself by just 11 to that is m. Yay! Because it's easier to go from log to exponential. All right, cool. There's going to be a whole little section, the homework in there. There's going to be a little section on the test, or the final, and the quiz for that. Okay. Trying to think of this in. So freaky stuff. What's up?
Is it going to have us also solve it? Like say it's saying log 11m equals 1.4. It'll tell us to then say solve for m after.
Yeah, sure, you could do
So
it.
you reverse.
Yeah, you could rewrite that. There's a way you could take this. So you could have like log base 2 of x equals -4. And it says solve for x. So how would you do that? The base to the power equals the input. And choosing -4th is
1 over 8.
1 over.
8. Oh,
1/16.
I like that. I said 1 over. She said it's still 8. Conviction. I love conviction.
So where are we going to do the problem on top?
Say again?
You could do that.
Yeah. So this is given. If I say solve this.
No. He's asking if
equals 3.
Oh, that one. Yeah, I don't know if we can get there today. I was hopeful. We're still a little bit off from really using these to solve equations. Because you have to understand the properties of logarithms to be able to use them to solve an equation. I can solve this equation because I know that the inverse of this is an exponential and I know how to write it given this. You guys see that? So it's almost like I'm not applying the inverse, but I am sort of using the inverse because it's another way to write that same statement. You guys kind of with me? Given that statement, I can rewrite it and then I know the answer. Because I know these are inverses of each other, a way to rewrite each other. Okay. So I think the last thing I want to talk about today, let me see if you guys can take this. Okay. So, it's 9 times 27. You with me? Let me see if this is enough to get this property understood. The derivation looks disgusting, and maybe I'm going to do it anyway. Well, we'll start here just to get a little motivation for this rule. Logarithms have, like I said earlier, the same rules for simplifying as powers do, because logs are powers. So when I multiply things that have the same base, and these do have the same base, don't they? 9 is 3 to the
Second.
27 is 3 to the third. When I multiply things with the same base, what would I do with their powers? Add them. Right? You guys with me? That's like, ooh. But yeah, okay, good. So what's really going on here then is log, what I just said, I'm going to prove it a little. Let's do this first. This is 3 squared times 3 cubed, right?
Right.
So this is log base 3 of 3 to the what?
5th power.
5th power. So the answer, no matter what the hell freaking shit I do, has to come out to be 5, right? Now the reason I'm about to do freaky shit is because it's not always like this that I can do this. Who knows what the hell's going to be in there? So I have to know how to do it in general. I just want to start with something that we know the answer. So what I'm saying is, if a log is the power on something, and you're telling me that I would add these guys' powers, is exactly what we did. Another way to write this product is to say when I multiply things with like bases, I add the powers. Because what's this represent? This represents the... What does a log represent? What do I keep saying?
Cube.
The log represents a power, right? So this is the power on 3 to make 9. This is the power on 3 to make 27. And we said, well, what should we do with those powers? We should add them. So it's not that big of a leap to realize, and this is so weird, because you guys are like, how did you make multiplication become addition? I didn't. This says, what's the log on the result? Well, wouldn't that be the addition of the powers on both? That's exactly what we did. What is log base 3 of 9?
2.
2, because 3 squared is 9. Log base 3 of 27? 3. 5, the same damn answer we got there. Actually a little quicker. So the general rule that we just did, the first property of logs is if I have log base b of m times n, I can make that log base b of m plus log base b of n. Now that is so different from anything we've ever done before. It is. I really hope you understand why it makes sense. Logs are powers. So whatever I would do with the powers, I actually would do with the logs. And it comes out the same. Okay? Alright, so that's the first rule. Second rule comes right after that. What the hell do you think you do if it's log base b of m over n? So yeah, you subtract when you divide. You subtract the powers when you divide, right? So this will be log base b of m minus log base b of n. So real quick, concrete application of that second property, right? It's always nice to have concrete stuff to look at. So if I had log base 4 of what you got, Jeff? I don't know. Let's do... Oh, I know. I know what I'm going to do. Took me a second. Don't really need this parenthesis, but too bad. Can you do either one of those?
No.
What's log base 4 of 3? What do you raise 4 to make 3?
Don't know.
I don't know, shit. But how can I rewrite this? This is the difference of two logs. When you subtract powers.
So log 4 with 4 gives over.
I love it. The biggest mistake I see is somebody writes this. Now that completely does not make sense. You cannot take that subtraction between these things and make it become division between those two things. You can never, ever do that. And that's not what this says. This says the log of this minus the log of that is the same thing as the log of division of those two things. I didn't make subtraction become division. But the idea makes sense because when do I subtract powers? When I was dividing the things I'm looking at. That's exactly what that says. Yeah?
Was one of the one that you exited out equal 1 to the power of 48?
No, be careful. You can't cancel these out.
No, I'm saying like it won't work. Oh, like no.
Okay. So like if I had square root of 7 over square root of 3, I can't cancel the square root symbols out, right? So this is a symbol of something. I can never cancel it out. But what would this be? I can actually do this now.
16.
Well, it gives me 4, 16, which is 2. Yay.
That was great.
All right, smartass. Yeah.
They have a different base. Now it's log 4, right?
Yeah, now if they had a different base, it would be a lot like you have to have the same root to do stuff with it. If these have a different base, you couldn't combine it. That's a good point. They have to have the same base. So that would be a lot like, like over there, if I have 3 cubed times 3 squared, that's like the 27 and the 9. But if I had 3 cubed times 4 squared, can you combine those? No, you'd have to actually figure out what number that is. And so that would be related to the bases being different. So if the bases on the logs are not the same, I can't do shit with it really. Unless I can do something with each of them separately. Cool, good question. Okay. So here's the most important property that actually directly relates to how to solve this thing. So maybe we got there. Let's see. Maybe we got there. This comes right off of property number 1. So if I have, here's property number 3. If I have log base b of m to some power. This is the most important property of logarithms. And they're all important. This just happens to be a little more important. Let's see, how the hell do I use property number 1 to help me with this thing? Property number 1 is all about what operation inside. And what operation do I have inside? I have exponents, which are base of multiplication. So I can write this as Log base b of m times m times m. How many times?
How many ever p is?
Good. P of them. Stay with me now. I'm doing the derivation now. You never do this middle work, dear guy. I'm just showing you why it works. So that can be written as this. There's pm's in a row. That's what m to the p power means. And then what does this property say I could do? Like I said, I have log base b of m plus log base b of m plus. And how many of these do I have? B of them. So if I had 3 of them, I could write that as 3 log base b of m. If I had 5 of them, I could write that as 5 log base b of m, because I could just collect them. How many do I have? P of them, so I can write that as p log. So it's plog. Yes, sir.
What if they had different logs? Like it was log 4 versus log 3, for example.
Man, if only I would have talked about that.
Would you have?
Oh yeah, I did talk about that. Yeah, sorry I'm being, but I just feel like doing it. All right, paying attention is good again. So now look what everything else is based on properties of powers. It still is. What do you do with the powers when you raise something with a power to a power? What do you do with the powers?
Adam?
X squared cubed.
Boy, those
Raise something with a power to a power. Multiply.
Yeah.
So I'm raising something with a power to a power. I'm going to multiply the powers. What are my 2 powers up here? That's a power, and that's a power. So I'm raising something with a power to a power. I multiply the powers. But better than that is exponents on the inside can come out front. That's basically all it did, right? So never do the middle stuff. That's why it works. So, real quick example. Oh, let's see, what can I do? You guys don't realize this yet, but we can now solve this. Right? You guys don't realize it. It's all right. So if I had, well, almost. If I had log base 7 of x cubed, how could I rewrite that?
3 log 7x.
Good. Those are the same thing. Cool. That was exciting. Okay, not too bad. So let me show you one thing. We'll solve this damn formula finally. There's just one thing we need extra to be able to do that. And then we'll call it a day. Yes, especially the last part. One thing I got to show you. This is related to the question somebody had earlier. How do I do log base 7 of 11 on my calculator?
Yes.
Right? And you're going to find that button, and you're going to let me know. You found it?
Yeah.
Let me see.
It doesn't work on the older one.
Not maybe.
That's 8 years bad luck. Make that what you think. You found it? Sure. You just punch the buttons.
You have it already?
Look at you. Kick the ass.
Alright.
And you got the backlight and everything.
I would say one.
Alright. So the rest of us, poor little peons, let's figure out how to do this. It's called the change of base formula. If you look at your calculator, do you see anything that looks like related to what we're talking about right now?
Yeah, the log button.
You see a log button.
Yeah.
Now,
Where?
Yeah.
It says, well, mine, yours is.
side note. Okay, now stay with me. Stay with me. I know we're all getting antsy because it's 12 o'clock, but it's too bad. There's one root that I don't have to put a number on because we know what it is, and that's the
Where?
square root. Right? So if you see a root without a number, I know that the number really would be 2. If I see a log without a number, good. It's called the common log, which is log base 10. Because our number system is based on 10. It's the most used log. It's the log we use to figure out Richter scale. Right? If you had an earthquake, 8.1 earthquake, pretty damn powerful. That's dealing with powers of 10. Right? That's what that relates to. That's powers of 10. So that would be log base 10. So when I see log, that means log base 10.
On the calculator?
Yeah, so your calculator, on the face of it, and the one that's not too new, can do log base 10. It can do something else too that we're not to yet, but log base 10 can definitely do. So if I put in there, try it in the calculator, if you see your log button, hit log 100. And why does that make sense? How many 10s do you multiply to make 100?
2.
There you go, so it makes sense. So that log without a base means base 10, just like a root without a number means base 2, index 2. Those are the most used roots and logs. Okay, good. So if our calculator can do log base 10, but the question is log base 7 or something, and I don't have a newer one, right?
It's over it. You can do it too.
Really?
Not the.
Let's do that.
That's the
I still want to show you this formula anyway. Whose class are you in? And how much does he let you use the calculator?
All the time.
Yeah. So if I want to know what's log base 7 of 11, what's a good guess for that? In between what and what? In between 1 and 2, probably closer to 1. Get out of here. Well, it's not right. That's why it's freaking out. Is it 0.845? It can't be right. It's got to be at least. It's got to be bigger than 1. So what is that? I don't know. So what do we call it? X. Now, how can I rewrite this? Stay with me now. 7 to the x equals 11. Now here's the power of that last property we talked about. Stay with me. I could take the log of both sides, which really means log base 10. Why would I do log base 10? Because that's the one that's on the face of my calculator, right? It's not hidden in some menu or maybe not even on my calculator. So if I take log base 10 of both sides, why is that good? I mean, where's my variable in that little equation? Where's my variable? It's up here. Can I solve for it? No. What would I have to do first to be able to? I have to get it down from there, right? Yeah. So like if it was on the denominator, I'd multiply by it first. I've got to get it out of there. If it's in the square root, I would square sometime to get it out of there. I need it out of there. What's the beautiful property of logs we just talked about? This power comes down. So x equals log 11 divided by log 7. This is a number. This is a number. Just like square root of 7, square root of 11, right? The logs don't cancel. Be careful. Yeah.
You could also use the pen, right? Same thing?
Good. We're not there yet.
Okay, I'm
Yeah.
just saying. Okay.
Natural logarithm. We're not there.
Okay.
You got stupid natural log cabin jokes floating around. It's really poor representation of math jokes. There's better ones. So what that really means, x was our original question, so it is this. Let's do log 11 divided by log 7. Be very careful. If your calculator opens a parenthesis, be sure to close it. Depends on which kind of calculator you have. And it better be 1 point
1.232.
something, yeah. Good. Closer to 1, between 1 and 2, 1.2, blah, blah, blah.
2322.
Cool. So if I did 7 to that power, what would I get? If I raised 7 to that power, I would have to get 11. Good, because that's what that means. Now, so I told you the last thing I want to show you this one thing. Now let's solve this so I can take over the world. Stay with me now. I want to know how long it was going to take. Remember, it was 6 minutes. We got about 700 more bacteria. So I want 15,000 more bacteria. So obviously it's going to take a little bit longer, huh?
15,000.
Yes. So I want 15,000 more than what I have currently. That would give me up to 18. How do I solve this equation? What's the first thing I should do? Where's my variable? Where's the term that has my variable? This piece has my variable, so what should I do first? Divide by 3,000. Yeah. So just like if it was a square root of 2 or whatever, I'm going to divide by 3,000 first, and then I can do what I have to do here. Same thing as always. Math likes to do that. So if I divide by 3,000, yeah, I get 6 equals 2 to the t over 20. My variable is stuck. If it was stuck inside of a cube root, I would cube. But what do I have to do here to help my variable out? Yeah, I've got to take a log. Both sides.
So now it goes T.
And what am I allowed to do?
T divided by 20.
Good. This power can come out and multiply by the other power. It's a property. The power can come down. See, so now we got everything we need to solve equations with exponential functions in them. We just got log at some point to get that variable back down. So now I get log 6, whatever number that is, equals t over 20 times log 2. Then you
Divide them.
10 times 20.
yeah, I can multiply by 20, sure. And divide by, no, not 2. Yeah, divide by log 2. Somebody help me out. What is that? 20 times log 6 divided by log 2.
I don't know if it's right. 51.6.
Sounds about right. Good. That's what I was expecting. 51 point something.
Yeah, 51.69925.
So about 51.7, we'll say. So less than an hour later, 3,000 E. coli will become 18,000.
But you need the calculator for that.
Definitely, holy shit.
Okay.
I mean, I can approximate it, but I want to know the exact answer. So, oh my God, we did a lot today. We actually got up through section 14.4.
Through.
Holy crap. Right? 14.1 through 14.4. And to be honest, we did a little bit of 14.6 at the same time.
Was already up on the math lab then?
No, I got to do that.
You still haven't done it?
No.
Apparently not. I just said I didn't.
What's your note? Because I can't go home and start my homework.
What's that?
My note here.
Oh, right there. So if you want to do, so do 20 times log. Sure. 6. So it's really easy. You got to close that parentheses before you continue dividing.
By 11 o'clock,
Log 2.
and you do homework, and then get up at 6 to do it all again.
Yep. There's your 51. Okay. Yeah. So it all depends on when I can do it.
I'll just study and prepare to.
Good. It's a good idea. Okay.
Is it like 21 centimeter or just like 24?
Oh, for the correct. I said on the test, it said take it out 3 places. So that's
So it
fine.
doesn't have to get
Thank you.
Can you set up the online as soon as you get a chance?
Oh yeah. Yeah. I'll do it right now. Okay. Oh yeah. Okay. I can do it right when I get in my office.
Thank you. Log 6 divided by
So 20.
need to use it.
Yeah. Oh yeah. 20. Close. Good. There you go.
Is there any way I can do that, like,
No.
log?
Nope.
Okay.
Not really, because you got to know what do you raise 10 to get 6? I don't know. Right? This means the power that 10, there's an understood 10 here. What do you raise 10 to get 6? Yes. So whenever you see a log, it's just like a root without a number is the square root. We just know it. A log without a number is the 10th log, the log base 10. This is most commonly
Debating whether negative. I was confused about this one. Was I not supposed to? Like I don't know.
You divided the 4 out.
Yeah, and then did completing the squares.
Sort of. Let's see. And that's just where did the 4 go? in the middle.
Oh, I left. I took it out, but then I plugged it back in at the end. That's, but I remember that.
Gotcha.
I know I
That's
did that. But is that the
the
problem?
ability to do something with that 4 there. You know how to
So
do
I
things
should have
is
showed
something
that.
you need.
So I should have showed that.
The only reason I would ever, because I told, this is completely fine if you're like somewhere you just got to get the answer. But the only time I take points off is if it's something you're going to need to be able to do, so that you're able to do even worse
So what
things
would have been
later.
the right process?
Leave the 4 in, but factor it out of the way. Take the 4 out.
So just put a great, just.
So then when you add 9, you would at the same time subtract 36, right?
Oh, so.
It's just that idea of balancing correctly that you have to get now. In case further along, you got that idea of it just worse.
So even though I'm like, I kept the 4, I had the 4 the whole time, but I didn't show that I multiplied back in, it didn't count.
Yeah. Well, because there's nothing that allows you to do what you did algebraically. I personally, this is the way I would do it just to get there. But I need to make sure you can do this, you can balance correctly, because that idea is used.
That's what you wanted.
That idea is used in a lot of different areas in math. So if you don't get it down now, you're going to suck wherever you go.
That makes sense.
Yeah. Cool.
Lovely. Let me think of one other one I had a problem with.
This stuff.
Oh, for 1F, it says solve, so.
Be sure to find all solutions. How many solutions should there be?
More than
3.
that.
So subtract 27, factor, you get the big dude that you can use quadratic formula on. When we do that, we only get the reals, but now that we've learned complex, we can go back and we can solve and get all the answers. The one real answer.
So really, it's solve.